Welcome to How to Succeed in ECE Without Really Trying. I'm Dr. Linda DeBrunner, and today I'm going to work through an example of cascaded op amps. So here's the circuit. Initially it looks pretty complicated because it's got two op amps in it, but when we look at it further we see that it's just two separate stages that can be analyzed separately, and then we can combine the two transfer functions. So the first thing we'll do is let's look at the input half, okay, going from this input, Vn of t, over to this point here, which I'm going to call V1, okay, V1 of t, and later on it'll be V1 of s. And so then we're going to look at another block going from here to here, going from V1 to V out. So if we can do that, we can write H of S is equal to V out of S over V1 of S times V1 of S over Vn of S, and that will give us our desired gain. Okay, so let's look at the yellow block first, the first half. There's our circuit. Now remember, we have three things we have to know about op amps. The input current going into each of these terminals is going to be 0. We also know that for negative feedback, this node and this node are going to have the same voltage. And the third thing is we want to do nodal analysis at the input terminals. So let's go ahead and we'll write an equation right here, and we'll write an equation right here. So at the positive terminal, the equation is very simple. We just say V plus is equal to ground, which is 0. Okay, at the other point, the the inverting terminal, we would write V minus Vn over 1 k ohm, which is 1,000, plus V minus V1 over 1 over S times 9 times 10 to the minus 9th, plus V minus V1 over 10 k ohms, which is 10,000, plus 0, the current going in here, and that will be equal to 0. So we can write this, then we can now take this and do some algebra, and we'll end up with, I guess we should plug in first our zeros and multiply through by minus 1. We'll end up with Vn over 1,000 plus V minus over 10,000 plus V minus over 1 over S times 9 times 10 to the minus 9th equals 0. Okay, now we can do some algebra. Here it is. First thing I would do is multiply through the whole equations by 10,000 to clear the denominator, and also go ahead and flip the S term so that we have it we clear that denominator as well. So we end up with 10 Vn plus V1 plus S times 9 times to the minus 9th times 10 to the 4th, which is 10,000. And then we end up with this being 10 Vn plus V1 times 1 plus V1 times S times 9 times 10 to the minus 5th. You can then solve for that transfer function, which I'm calling H1 of S, V1 of S over Vn of S, and that will give us 10 over 9 times 10 to the minus 5th S plus 1. Okay, now we can do the second half. So again, let's look at this part here, and we end up with those three things we do. In at the terminals is 0. V minus and V plus are equal for negative feedback, which is always our case. And then also we do nodal analysis at these nodes. So at V positive, we end up with 0. And remember, it's not always going to be 0, so you do have to stop and think about it. And then we also at V minus, we're going to have V minus minus V1 over 12,000 plus 9 times 10 to the minus ninth. Oops, sorry. That's my mistake I typically make. 1 over S times 9 times 10 to the minus ninth. I catch it pretty often, but always watch for that. Plus V minus minus V out over 96,000. A K is 1,000, of course. And that's equal to, plus 0 is equal to 0. So the first thing we're going to do is we're going to go ahead and deal with this denominator here. So to clear the denominator, we flip that bottom part of the fraction. We end up with 9 times 10 to the minus ninth times S times V1 plus over 12,000 times 9 times 10 to the minus ninth S plus 1. And then we'll move the V out over 96,000 to the right-hand side. Then we will go ahead and we'll take the ratio, and we end up with this. Simplifying the terms gives us these values, and we will call that H2 of S. Now that we know H1 of S and H2 of S, we can just multiply them together to get H of S. And so we put that all together, do the multiplication, and we'll end up with this number, 0.00864 times S over 9.72 times 10 to the minus 9th S squared plus 1.98 times 10 to the minus 4th S plus 1. And that right there is the transfer function. So we can go ahead and use MATLAB to plot it similar to the ways we've done it previously, and we end up with a frequency plot, okay, that shows what's happening. Again, we have the magnitude and the phase. If we want to look at it further, we can look at the phase, look at the magnitude. I blew it up here. And we want to find the 3 dB down points from the maximum value. And if we look, it looks like the peak right here, and of course we're estimating, of course, but it looks like that peak is right at 10 to the 4th radians per second. And we can put that in frequency by dividing by omega by 2 pi, and that gives us 1.5915 kilohertz. The bandwidth is going to be approximately those 3 dB down points. So you just count 3 dB down. It's almost impossible on this graph to do that, just to read it. But I did it on MATLAB, and I just blew it up a little bit and used the pointing function on MATLAB. And you end up with 15,000 minus 6,800, which gives us about 8,200 radians per second. We can divide that by 2 pi, and we get about 130.5 hertz. So that means that the passband peak is at 1.5915 kilohertz, and the width of the passband is about 130.5, and that should be hertz, yes. So it's very narrow.